This video is on section 5.3, which is double angle, power reducing, and half angle formulas. Here are the objectives for this section, and basically it's just applying those three types of formulas. Now I'm not going to spend a lot of time on these slides here. Basically, these slides show you how the double angle formulas are derived. So basically, we will start with this and end up with this. Take some time and you can look at each of these different slides. So this is the this is how cosine of 2 theta is derived. And you'll see that we will, there's one more, we will deal with these three versions of cosine of 2 theta. And then finally, here is the double angle formula for tangent of 2 theta. And we'll end up here. Okay, so you're welcome to look at how these are derived. But when it comes down to it, these are the formulas that we will use. So there are these three here: sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. You'll see that sine of 2 theta and tangent of 2 theta have just one formula, whereas cosine of 2 theta, it has three choices. And depending on what you are doing, you will want to choose one of these three options over another. It might just help a little bit. So these double angle formulas can be used with angles other than 2 theta. For example, if I have cosine of 4 theta, then so the original formula is cosine of 2 theta is equal to 1 minus 2 sine squared of theta. So in this case, 2 theta is really 4 theta, so we need to multiply theta by 2 in this case. And then the same thing, if this is just a, we'll divide everything by 2. Okay, so there are different ways you can use and apply these double angle formulas. But let's jump into some examples. Okay, so here is our first example. And we are given sine of theta is 5/13. And we are given that tangent of theta is less than 0, which means tangent of theta is negative, and we want to find sine of 2 theta. Well, we need to figure out which quadrant we are dealing with. So sine of theta, we know sine of theta is positive in quadrant 1 and quadrant 2. And we know tangent is negative in quadrant 2 and quadrant 4. So we need to identify the overlap, and the overlap is in quadrant 2. So I'm going to use this given information and draw a triangle in quadrant 2. So this will be theta. And we're just going to use a little bit of SOHCAHTOA. And we are given sine, so the opposite is 5 and the hypotenuse is 13. You should be able to use the Pythagorean theorem to find the missing side. And when you do, you'll find that x is positive or negative 12. Well, in this case, in the second quadrant, sine and cosine are negative. Cosine is negative, so this should be a negative 12. Okay, so be cautious of your sign there. Now, the reason we had to do all of this is because the formula for sine of 2 theta is 2 times sine of theta times cosine of theta. And we were only given sine of theta in our problem. So we had to use that information to find our triangle so that we could find any of the 6 trig functions, including cosine of theta. So now we can use this triangle and plug in the given information. So sine of theta was given to us as 5/13. Cosine of theta, applying SOHCAHTOA, gives us -12/13. So remember, when you multiply fractions, multiply across the top, across the bottom, and you should end up with a -120 over 169 for the final answer. Let's try another one. Okay, so here we are given tangent is -5/4. So we know that tangent is negative in quadrant 2 and in quadrant 4, but then it says, hey, theta is in quadrant 4. So the tricky part's done for us. Let's just go ahead and draw this triangle in quadrant 4. So given this information here and applying SOHCAHTOA, tangent of theta is -5/4, which means one of these values has to be negative, and this is heading in the downward direction here, so this will be negative. And then you should be able to apply the Pythagorean theorem to find the missing side, which is the square root of 41. Okay, now cosine of 2 theta, when we're dealing with cosine of 2 theta, we really have 3 options. So any of the 3 options are perfectly fine. Whichever one you choose is up to you in this case. So I'm going to choose 2 cosine squared of theta minus 1 here. All right, now the thing you need to be cautious of is that this is squared. So remember, we can also write this as 2 cosine of theta quantity squared. That's the same thing as what's written in the red, okay? So we need to find what cosine of theta is, and we will refer to this purple triangle over here to do so. According to this triangle, cosine of theta is 4 over the square root of 41. And I'm going to square that and then subtract 1. I'm not going to rationalize this denominator because if I square this, I square the top and square the bottom, and I end up with 2 times 16 over 41 minus 1. So I can put the 2 over 1, multiply across the top and across the bottom. This gives me 32 over 41. I'm going to rewrite 1 with a denominator of 1. 1 can be written as 41 over 41. When I subtract this, I end up with a -9 over 41. Okay, so example 1 and example 2 will show you one type of problem that you will see with these double angle formulas. Just like we've done previously, we will have to verify the identity. Now, you have a lot of choices here, and before I came up with the method that I'm going to show you, I went through a lot of scratch paper on this one, I'm not gonna lie. So when I show this to you, I originally took lots of different avenues and I wasn't getting anywhere. So I scribbled it out and tried something different. That is very common. These just take practice, okay? Now, I'll tell you what I started with. I started originally with the left-hand side and used the double angle formulas, but I just wasn't getting anywhere where I wanted to. I had too many choices for this cosine of 2x. So what I ended up doing is I ended up actually starting with the right-hand side and manipulating the right-hand side to get to this. Okay, so I'm going to just rewrite this right-hand side. All right, now what I did originally with this right-hand side is I took the conjugate and multiplied by the conjugate of the denominator, but that didn't get me where I needed to go. So I tried the conjugate of the numerator, and this seemed to do the trick. So I multiplied the top and the bottom by the conjugate of the numerator. And again, you guys, it took me a while to come up with this. So what I did now is I FOILed the top and the bottom. Okay, so when I FOILed the top and the bottom, I got the following. On the top, I got cosine squared of x plus sine squared of x. All over FOILing the bottom, cosine squared of x minus 2 cosine of x times sine of x plus sine squared of x. All right, now from here, you know, it's helpful to have a list of all the identities in front of you, because if you do, you might notice that cosine squared of x plus sine squared of x is in fact an identity. In fact, it is, cosine of 2x, which is great because that's what we want in the numerator. Now in the denominator, I have, let's see here. Sorry guys, I have a typo here. This should be a minus. That's why we get this. I apologize for that. Okay, then in the denominator, this plus this equals 1. So I have 1 minus 2 cosine of x sine of x. And maybe right away you notice this is a double angle formula. So we end up with cosine of 2x over 1 minus sine of 2x. And this is what we wanted. Woo-hoo. Let's verify another. Okay, so this one, I started off with the left-hand side. And sine of 3x is not a formula we have, so what we need to do is we need to come up with another way of writing sine of 3x. And we're going to go, the approach we're going to take is we're going to go back to some formulas we've already used. And I'm going to write sine of 3x instead as sine of 2x plus x using a sum formula all over sine of x. Now you might want to glance ahead at the right-hand side so you can see what we are working towards. Okay, so using the addition formula here, this becomes sine of 2x times cosine of x plus cosine of 2x times sine of x, and everything is still over sine of x. Okay, here, double angle, double angle. Sine of 2x, no problem at all. There's only one option. But for cosine of 2x, we have 3 choices for this. And this is where it gets a little tricky because you have to kind of think ahead a little bit and try some things to see if it's going to get to where you need to be. And it's tricky. So applying the double angle for sine of 2x, I end up with 2 sine of x cosine of x times this cosine of x plus. Now over here I need to come up with some choice for the sine of 2x. Just play around and see what you get. I chose 2 cosine squared of x minus 1 times this sine of x here. Everything is over sine of x. Okay, now looking at this, a couple things stand out to me. When I multiply this, I get cosine squared of x. And then I can also distribute over here. So I'm going to kind of simplify a little bit. And when I do, I have 2 sine of x cosine squared of x plus, distributing over here in the second term, 2 sine of x cosine squared of x minus sine of x all over sine of x. Okay, here I have some like terms. This and this are like terms. So I can combine those. And when I do, I get 4 sine of x cosine squared of x minus sine of x all over sine of x. Now look ahead at what we're trying to get to. Now on the right-hand side, I don't have any signs. I don't have a fraction. So I might want to see if I can do something with all of these signs. And in fact, I can. I can factor out sine of x in the top. So I'm left with 4 cosine squared of x minus 1 all over sine of x. And then the sine of x's cancel, and it leaves me with 4 cosine squared of x minus 1, which is what I wanted to achieve. Okay. We're now going to jump into another type of formula, which is the power reducing formulas. These power reducing formulas, or really all of these formulas, they will occasionally pop up in calculus. So you will want to be familiar with them and, be able to kind of recognize them when they come up, because when you get to calculus, you will need to know how to use these. So basically, the reason they are important, you'll find, is leading to calculus, we can't integrate something like this, but we can integrate something like this. And I know that doesn't mean anything now, but that's why we are teaching you these formulas. Okay, so we're just going to jump in and I'm going to show you how to utilize these. Okay, so you'll see something like this. It will say write sine of 2x to the power of 4 in terms of the first power of cosine. Now what this means is you want this to end up being something with cosine in it. Okay, and there can be a lot of them, but cosine cannot be raised to any power other than 1. Okay, so we need to work towards cosine. All right. Now, I want to remind you that sine of 2x to the power of 4 can also be written in this way. Okay. I can also write this as sine squared of 2x squared, because that is also to the power of 4. Now remember, I'm not squaring this argument. Okay, the argument is not being squared. That stays as is. So if I am starting with this, because it's the same thing as what we're starting with, okay? So this here is the same thing as this, okay? I need to use a double angle formula. So I want to remind you that the formula is sine squared of theta. This is equal to 1 minus cosine of 2 theta over 2. So the thing we need to be cautious of is the formula has an argument of theta, but we have an argument of 2 theta, or 2x in this case. So when I apply this formula here, we end up with the following. 1 minus cosine of 4x all over 2. And all of this is squared because of this exponent right here. Okay, so we are going to square the top and the bottom. Now when I square the top, I have to FOIL this out. I can't just distribute the square because of the minus sign in between the two terms. If it were multiplication or division, then I can. So I square the top and square the bottom. Now I have to FOIL this out. So when I FOIL the top, I end up with the following. 1 minus 2 cosine of 4x plus cosine squared of 4x all over 4. Now, I want my answer to be first powers of cosine. And I have an issue right here because this is cosine squared. So I need to apply a formula here to eliminate that cosine squared. Everything else is fine. Now, another thing I'm going to address is this denominator of 4. If I have a denominator of 4, recall it's the same thing as multiplying everything by a fourth. Okay, so I'm just going to take that and move that out in front. And then I'm going to apply the formula here. So I keep 1 minus 2 cosine of 4x, but I need to apply the formula for this cosine squared of 4x. So applying this formula, be careful of the argument, it becomes 1 plus cosine of 8x all over 2. So now I'm going to distribute this 1/4 to everything. And I'm also going to take this out of the fraction using the Hart method. So I get 1/4 minus 1/4 times this term is 2/4 or a half cosine of 4x. Remember, you don't touch the argument. Plus 1/2, so this times a fourth is 1/8, plus 1/8 cosine of 8x. Again, not touching the argument. I have a few like terms, so when I combine this, all is said and done, and my final answer is 3/8 minus 1/2 cosine of 4x plus 1/8 cosine of 8x. Now, I know this is my final answer because this is written in terms of first powers of cosine. Notice cosine is not raised to any powers. I cannot combine these cosines because they have different arguments. And there you have it. Let's try another one. In fact, maybe you want to try this one on your own. So now I am starting with cosine of x to the power of 4, and again, I want this to be first powers of cosine. So I know that cosine to the power of 4 can be written as cosine of x squared times cosine of x squared. And so what I can do here is I can use the formula on this as well as the formula for this and multiply them together. And when I use that formula, I have 1 plus cosine of 2x over 2 times the quantity 1 plus cosine of 2x over 2. Then I can simply multiply across the top by foiling this and multiply across the bottom. When I foil on the top, I get 1 plus 2 cosine of 2x plus cosine squared of 2x all over 4. Now this kind of leads us to the same place we were in the previous problem. This is not a first power of cosine, so I need to use a formula here to reduce that. Also, like the previous problem, I'm going to move this 4 out in front, so I end up with 1/4 times 1 plus 2 cosine of 2x, so that stays the same. But applying the formula and being cautious of this argument, I get 1 plus cosine of 4x all over 2. Okay, so everything here is in first powers of cosine, which is great. So the only thing I really need to do is break this into 2 separate fractions and then distribute this 1/4. And when I do that, I have 1/4 plus 1/4 times 2 is 1/2 of cosine of 2x plus 1/4 times 1/2 is 1/8 plus 1/4 times 1/2 cosine of 4x is 1/8 cosine of 4x. Combine like terms like we did in the previous problem, and we'll get 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x. And this is our final answer. Okay, so now let's touch on half angle formulas. This is the last type of formula we'll see in this section. And here they are. All right, so you will notice that these each have a radical, and they each have a plus or minus in front. And the plus or minus is determined by the quadrant of our angle. Okay, so depending on the quadrant, we'll have either a positive or a negative radical. So you can also see that tangent of alpha divided by 2 has a couple different forms, and we will address that when they come up. So let's jump into our first example. It says, use the half angle formula to find the exact value of this. Okay, well, we're dealing with sine. So we know that sine of alpha divided by 2 is plus or minus the square root of 1 minus cosine of alpha all over 2. Okay, so notice that in our formula, we are dealing with alpha, and alpha is divided by 2. We can write alpha divided by 2 as half of alpha. So we need to figure out what 5 pi over 12 is half of. Well, half of what gives us this? That would be 5 pi over 6. So our alpha is going to be 5 pi over 6. Okay. Now, 5 pi over 12, this angle is in quadrant 1. And we know that sine is positive in quadrant 1. So I'm going to use the positive square root. Okay, so let's put this all together. And we'll find sine of 5 pi over 12 is equal to the positive radical of 1 minus cosine of 5 pi over 6, all over 2. Okay, well, we're just going to truck along, and now we need to evaluate cosine of 5 pi over 6. Well, cosine of 5 pi over 6. 5 pi over 6 is not quite 6 pi over 6, which means it's in quadrant 2. The reference angle is pi over 6, so that is root 3 over 2, 1/2. In quadrant 2, I know that cosine is negative. So in this case, cosine of 5 pi over 6 is the negative square root of 3 over 2. So I'll have 1 minus the negative square root of 3 over 2, all over 2. And then we'll just continue to simplify. This becomes 1 plus the square root of 3 over 2, all over 2. I never want a fraction within a fraction. So in this case here, I'm going to multiply the top and the bottom by 2. Everything in the top gets multiplied by 2. So I have 2 plus, the 2 cancels here, leaving me with the square root of 3 over 4. Remember, when you have division of radicals, you can take the square root of the top over the square root of the bottom, and we will end up with our final answer of 2 plus the square root of 3 under a radical all over 2. Now, I know this is a little ugly, but this is the exact answer, or the exact value of sine of 5 pi over 12. Okay. Now, let's do another example, but this example is going to be in terms of degrees rather than radians. Okay, so the same thing here. Now you might want to remember, if we want to find sine of 165, you may want to look up what that formula is. So sine of alpha divided by 2, again, is plus or minus the square root of 1 minus cosine of alpha all over 2. Okay, so if we are starting with 165 degrees, we want to figure out what is half of something to be 165. Well, 330 degrees is half. Half of 330 degrees is 165. So that means our alpha in our formula is going to be 330. Now we have to figure out if 165, so here, let me write it this way. Sine of 165 degrees is equal to, now this here, 165 is in quadrant 2, and sine is positive in quadrant 2, so I know that I need the positive radical. Okay, 1 minus cosine of, we said alpha is 330 degrees, all over 2. All right, so we need to evaluate cosine of 330 degrees. So 330 degrees is in this quadrant here. It's not quite 360 degrees, which means my reference angle is 30 degrees, or pi over 6. So this is my corresponding ordered pair, And in quadrant 4, the y value is negative. So here, when I evaluate this, cosine of 330 degrees is the square root of 3 over 2. Just like the previous problem, we will multiply the top and the bottom by 2. So 2 minus the square root of 3 over 4. I can take the radical of the top and the bottom to get the square root of 2 minus root 3 all over 4. I'm sorry, all over 2, because the square root of 4 is 2. And there you have it. Okay, so this example is different than the others we've seen. So here we are given sine of alpha is negative. So let's evaluate this. Where is sine negative? Sine is negative in quadrant 3 and quadrant 4. All right, well, we need to narrow it down, and the way we narrow this down is by looking at this information. Alpha is in between 3 pi over 2 and 2 pi. Well, 3 pi over 2 is here, 2 pi is here, so this is quadrant 4, which means the overlap must be quadrant 4. Okay, so in quadrant 4, let's draw our triangle. This is alpha. I'm going to use the information given to me by sine. So in this, I know one of these is 7. This is 25. One of these has to be negative, and it's never the hypotenuse. So 7 is negative. Using the Pythagorean theorem, I can find the missing side is 24. Okay. So now we need to figure out the following. Tangent of alpha over 2 is... Okay, so one thing I want to point out is the following. If we want to find tangent of alpha over 2, we have 3 choices for this formula. And it's really up to you which one you want, okay? I am going to choose to work with positive values, so I'm going to use, and not a radical, so I'm going to use this formula. Okay, it's really a preference thing, all right? So when I plug in my information, I get the following. Sine of alpha was given to me. 1 minus cosine, I'm sorry, 1 plus cosine of alpha is 24/25. I don't want fractions within fractions. My denominator in the top and the bottom is 25. So I'll cancel this out by multiplying the top and the bottom by 25. So I have negative 7 over 25 plus 24. This gives me negative 7 over 49. 7 goes into each of these numbers evenly. So I end up with a negative 1/7. Now, it is wise to analyze why this answer is negative. And if I'm looking for a value of tangent in the 4th quadrant, I know that tangent is negative in the 4th quadrant. So I'm good to go. Okay, here is the last example. In this case, we want to verify the identity. It's pretty straightforward that the left-hand side is the more complicated side. Just like the previous verifying problems, this one I took a couple choices. Okay, so when I took a couple routes and it didn't work out the way I wanted. So here is what we're going to do. Now, looking at this here, when I look at this, a couple things stand out to me. And one of them is that this is a half angle formula. But the other is that this might require a power reducing formula as well. So, you know, it's really up to you which approach you take. First, I started with a power reducing formula and it didn't really get me to where I wanted. So then I tried half angle and that worked. So I'm going to apply a half angle formula to this. Okay, and when I do, I want to be cautious and I want to remember that this is really squared. So you can think of this as cosine of alpha divided by 2 quantity squared. So cosine of alpha divided by 2, recall, is plus or minus the square root of 1 plus cosine of alpha divided by 2, and this is squared. Now you will find, since you're squaring this, this sign is not going to matter because it's squared, and the radical will also go away because it's squared. Now I have tangent of alpha divided by 2. I'm going to use a half angle formula here, but you have 3 choices. So kind of look ahead to where you want to go, and you want something with signs in it. So I am going to choose to use this portion of that formula, sine of alpha over 1 plus cosine of alpha. And again, you guys, this is just going to take some playing. This equals, when I square this, I get 1 plus cosine of alpha over 2 times sine of alpha divided by 1 plus cosine of alpha. Well, what do you know? This is amazing because the 1 plus cosines cancel out. So I have sine of alpha over 2, which can be written as 1/2 sine of alpha, which is what I wanted. And this concludes section 5.3.